Hey everyone, welcome back. Before we dive into today's cosmic slow dance, I'm sending out massive waves of positivity and heartfelt wishes to every single one of you watching. Seriously, wherever you are in the world, I genuinely hope you're feeling fantastic, taking amazing care of yourselves, and staying healthy. That's the foundation for enjoying the incredible universe we live in. Now, get ready to look up at the night sky with fresh eyes, because that beautiful, familiar moon hanging there isn't quite as fixed as it seems. Here's a mind-bending truth that reshapes our understanding of Earth's closest companion. The moon is slowly drifting away from us. Yep, you heard that right. Right now, as you watch it shine, our moon is inching further out into space, year after year, century after century. It's not a sudden escape. It's a gradual, relentless retreat, a celestial waltz where our partner is slowly stepping back. Forget the idea of the moon eternally fixed in its orbit. It's on a very, very slow journey away from Earth, and this gentle departure has profound implications for our planet's distant future. So, how do we even know this? We haven't been measuring the moon's distance for millions of years, right? The key lies in an incredible feat of human ingenuity and precision left behind by the Apollo astronauts. During the Apollo 11, 14, and 15 missions, astronauts placed special corner cube retroreflectors on the lunar surface. Think of these as incredibly sophisticated mirrors designed to bounce light directly back to its source, no matter the angle. Back on Earth, powerful lasers at observatories like the McDonald Observatory in Texas or the Observatoire de la Côte d'Azur in France fire intense pulses of laser light precisely towards these reflectors. By meticulously timing how long it takes for that light pulse to travel the nearly 400,000 kilometers to the moon, bounce off the reflector, and travel all the way back to Earth, scientists can calculate the distance to the moon with astonishing accuracy, down to a few millimeters. Imagine measuring the distance to a moving target the size of a car hundreds of thousands of kilometers away and being accurate to the width of a pencil lead. By repeating these measurements over decades, scientists have built up an incredibly precise record. And the consistent finding? The round-trip travel time for the laser light is getting very slightly longer. This tiny increase in time directly translates to the moon being a little bit further away each time we measure it. The current rate? About 3.8 centimeters, 1.5 inches, farther away every single year. That's roughly the speed your fingernails grow. But why is this happening? What cosmic force is gently pushing the moon away? The answer lies in the powerful, daily tug-of-war between the Earth and the moon, the tides. You see the ocean tides rise and fall, but the gravitational pull causing them is actually doing something much more profound. The moon's gravity pulls strongest on the side of Earth facing it. This pull stretches the Earth itself slightly, solid Earth tides, which are small but real, and, much more noticeably, pulls the oceans towards it, creating the bulge of water we experience as high tide. Because the Earth is spinning on its axis much faster, once every 24 hours, than the moon orbits the Earth, once every 27.3 days, this tidal bulge isn't perfectly aligned under the moon. The Earth's rapid rotation drags the tidal bulge ahead of the point directly under the moon. Think of it like trying to pull a dog on a leash. If the dog is running ahead of you, your pull isn't straight back, but slightly forward on the dog. Similarly, the moon's gravity pulls back on this leading tidal bulge. This gravitational interaction has two major effects, locked together like cosmic gears. First, the pull on the leading tidal bulge acts like a brake on the Earth's rotation. It transfers rotational energy away from the spinning Earth. This is why our planet's spin is very gradually slowing down. Days are getting longer, but incredibly slowly, by about 1.7 milliseconds per century. Over hundreds of millions of years, this adds up significantly. Days were much shorter in the distant past. Second, according to Newton's third law, for every action, there's an equal and opposite reaction. If the moon is pulling back on the Earth's tidal bulge and slowing the Earth down, the Earth must also be exerting an equal and opposite force on the moon. This force doesn't slow the moon down. Instead, it gives the moon a little gravitational kick forward in its orbit. Because the moon is orbiting the Earth, giving it a nudge forward in its direction of travel adds energy to its orbit. When you add energy to an orbiting object, it doesn't speed up indefinitely. Instead, it moves into a higher orbit. Just like a spacecraft firing its engines to climb away from Earth, the moon is getting a constant, tiny push that causes it to spiral slowly outward into a larger, slower orbit. This transfer of rotational energy from the Earth's spin to the moon's orbital motion, mediated by the tides, is the engine driving the moon's retreat. The ocean tides are essentially acting as a friction brake on Earth's spin and a booster rocket for the moon's orbit. This process wasn't always this slow, though. Billions of years ago, just after the moon formed, likely from the debris of a giant impact between early Earth and a Mars-sized object called Theia, it was much closer to Earth. Estimates suggest it might have been only 20,000 to 30,000 kilometers away, compared to the current average of about 384,000 kilometers. Imagine a moon appearing 15 to 20 times larger in the sky. At that proximity, the tidal forces were immensely stronger. The Earth was spinning much faster too, possibly with days lasting only 5 or 6 hours. This combination, stronger tides and a faster spin, meant the energy transfer was far more efficient. The moon was likely receding at a rate of perhaps kilometers per year in those early chaotic times, not just centimeters. As the moon drifted farther away and the Earth's rotation slowed down, the tidal forces weakened, and the recession rate dramatically decreased to the slow crawl we measure today. It's a process that has been ongoing for over 4.5 billion years, gradually increasing the Earth-Moon distance and lengthening our day. What does this mean for the future? Well, the moon isn't going to vanish overnight or even in a million years. At 3.8 centimeters per year, it will take a staggering amount of time for the change to become truly dramatic for human experience. However, over tens and hundreds of millions of years, the effects will accumulate. The moon will continue to drift further away. As it moves farther out, it will appear slightly smaller in our sky. More significantly, its gravitational influence on Earth will weaken. The most noticeable effect will be on the tides. Tides are caused primarily by the moon's gravity. The sun plays a smaller role. As the moon recedes, the tidal bulges it raises will become smaller. High tides won't reach as high, and low tides won't fall as low. The rhythm of the ocean's rise and fall will become less pronounced. This will impact coastal ecosystems that have evolved around the current tidal range. Furthermore, the Earth's rotation will continue to slow down, making our days longer. While adding milliseconds per century is negligible now, over a billion years, a day could be significantly longer than 24 hours, perhaps 25 or 26 hours long. The moon's apparent motion across the sky will also slow down, taking longer to complete its cycle of phases. Solar eclipses will become rarer and eventually impossible. Total solar eclipses happen because the moon, as seen from Earth, is almost exactly the same apparent size as the sun. As the moon drifts further away, it will appear smaller. Eventually, it will no longer be large enough to completely cover the sun's disk, meaning total solar eclipses will become a thing of the distant past, replaced by only annular, ring of fire eclipses. Will the moon ever escape completely? The simple answer is no, not before the sun dies. The recession rate depends on the tidal friction, which itself depends on the Earth-Moon distance and the Earth's rotation rate. As the moon moves further away, the tidal forces weaken significantly. Simultaneously, as the Earth's rotation slows down, the drag causing the tidal bulge to lead the moon decreases. Eventually, Earth's rotation will slow down enough to become tidally locked with the moon, just like the moon is already tidally locked with Earth, which is why we only ever see one side of the moon. This means Earth will rotate at exactly the same rate as the moon orbits. One Earth day will equal one lunar month, about 47 of our current days. At this point, the same hemisphere of Earth will always face the moon, just like one hemisphere of the moon always faces Earth. The tidal bulges would then be fixed relative to the Earth-Moon line, no longer leading the moon. Without that offset bulge, the mechanism driving the moon away would effectively shut down. The recession would stop. The moon would settle into a stable, much more distant orbit, estimated to be about 1.5 times its current distance, and Earth would keep that same face locked towards it forever after. This state of mutual tidal locking is the ultimate endgame for the Earth-Moon system, a stable configuration reached billions of years from now, long before the Sun swells into a red giant and engulfs the inner planets. The Moon's slow departure is more than just a curious astronomical fact. It's a powerful testament to the dynamic nature of our cosmic neighborhood and the intricate interplay of gravity and time. It shows us that even seemingly permanent fixtures in our sky are engaged in an endless cosmic dance governed by fundamental physical laws. The tides that shape our coastlines, influence marine life, and have guided human navigation for millennia are directly linked to this gradual separation. The length of our day, a fundamental rhythm of life on Earth, is slowly stretching because of it. Studying the Moon's recession helps us understand the history of the Earth-Moon system, the evolution of planetary rotation, and the long-term fate of celestial bodies locked in gravitational embrace. It connects us to the violent birth of the Moon, the primordial Earth spinning like a top with a giant companion looming overhead, and projects us forward to a future Earth with slower rhythms and a more distant, smaller Moon. It's a humbling reminder that our perspective is just a snapshot in deep time. The Moon we cherish, the tides we rely on, the 24-hour day we structure our lives around, these are not eternal constants. They are stages in an ongoing, billion-year story written by gravity and friction. So, the next time you gaze up at the Moon, feel the pull of the tide, or simply note the passage of a day, remember the invisible, gentle push that's slowly carrying our celestial partner further into the cosmic dark. It's a silent, relentless change, a testament to the universe in motion, and a reminder that even the grandest celestial ballets unfold one tiny, centimeter per year step at a time. Thanks for pondering the Moon's slow farewell with me today. Stay curious, stay healthy, and keep looking up with wonder.